Okay, so this is the formula sheet for the test, or part of it anyway. And the reason I have this on here is because for question number three, we're going to use this equation. And let me describe this equation for just a moment. What this equation is describing physically is the phenomena of perspective, for example. If something is relatively close to you. It looks bigger. Like here's an example I always use in the classroom is you take a chair, right? Um, a chair is just is so big, and you could obviously measure that size. But if you put the chair further away from you, it looks smaller. All right, that's in artists' terms that's called perspective. And see what this obviously the chair is not any smaller. It just looks smaller because it's further away. What this equation does is it describes that. All right, so that's the idea. So L is the script L is the actual size of the object. Um, Pi over 180 is a constant. D is the distance to the object, and alpha is the angular size of the object. All right, so let's get to the problem for question number three. All right, so here's what it says. Um, Suppose the circular crater Tycho on the moon has a diameter of 85 kilometers, which actually we know that that's the size of Tycho. Could a person see this crater with the unaided eye? And we want to show your work for any credit. Um, the smallest angle that a human can resolve is at zero point 0.5 arc minutes. All right. Um, and what we're going to do is we're going to use the average distance to the moon as 384,400 kilometers. All right. So one of the things they're giving you what alpha is. All right. So alpha now in the equation that I just showed you a moment ago, alpha actually has to be in degrees. All right. So here it's given to us as zero point 0.5, right? Arc minutes, right? I'll write it like this: arc. Sorry, I didn't mean to do it like that. Oops. There we go. Almost. All right. Anyhow, I gotta choose the right size. All right. There we go. Arc minutes. I should have just used the single hash mark, right? That would have been much easier. All right, so convert that from arc minutes to degrees. We know that in 1 degree, all right. So I'm just going to use the symbol for degree. 1 degree, there are 60 arc minutes. So I'm just going to use the single hash mark. So remember, the single hash mark and the arc minute means the same thing. So this cancels this, if you will. All right, so this is a really small angle, and we could figure out what that value is. All right, so I'll do that real quick, and we're gonna put this all out. We need to do that. All right, so we take zero point 0.5. So this is like the limit at which the human eye can resolve something. Resolving is when you can tell that if there's two objects there, you can tell that there's two objects. So zero point 0.5 divided by 60. So this is just a very tiny angle. So the human eye can resolve down to about 0.008 degrees. All right, so that's really the number that we're looking for. 0.0083. We'll round it right about there. So it's point there. Let me finish that. There's our calculation. It's I'll just put it down 0.0083. All right, and it's degrees. All right, so we've converted to degrees. We've converted it to degrees. All right, so we know what alpha is in degrees, right? For the human eye, for the average human eye. All right. Well, yeah. My eyes are not good enough to see this. I would actually that's kind of the limit at which the human eye could see. I wear glasses, of course, so um, I would probably have to use binoculars to see this kind of thing. But at any rate, we're going to use this distance right here that they give us. Here, just slightly underline that. All right, and so here's our formula. All right, so our formula is script L. Remember, that's the actual size of this object is equal to pi over 180. Right, that's just a constant, pi over 180. Right, and that's 180, not 186. Sorry about that. Looks like 180. All right, very good. Gonna do this again. Okay, so pi over 180 times the distance, right? And so the distance here is 3844400. And of course that's kilometers, and times alpha, all right? And so we just figured out what alpha was. It's 0.0083 degrees. And by the way, this degrees and the 180 degrees cancel each other out. But and the other thing is since this is in kilometers, the distance is in kilometers, L will be in kilometers as well, which is really what we want. All right. So the question is L greater than um, greater than 85 or less than 85? Right. So this is, remember, if this is the limit at which the human eye can see, if this number turns out to be greater than 85, then the answer would be no. You can't see the crater Tycho. All right, which of course, I've got the answer right there. So let's see the limit at which the human eye could actually, what's the size of a crater on the moon that the human eye could see. All right, so it's this formula, right? We just have to figure out what L is. And we already have the angle in degrees. All right, so here's my, there it is right there. All right, so then I'm going to multiply that times the distance to the moon. So times 384,400. Right, so that's 384,400 kilometers. That's the average distance between the Earth and the Moon, because the Moon gets a little further from the Moon. The Moon gets a little further from the Earth and a little closer to the Earth because it's an elliptical orbit. But this is the average distance, and so we multiplied that, and then now we have to multiply that times pi. I kind of did this in reverse, so I multiplied this number times the distance, and then times pi. So times pi, and then divide the whole thing by 180. 180. All right. So this is going to oops. I had the answer just a second ago. Sorry. So the answer was. Did you see it's right there? I hit equals twice, which is, I hate this calculator. It's just convenient because I'm doing this on the computer. Anyhow, the answer was, do you see it right there? I got it, 55.9. All right, so 55.9, that would be the limit at which the human eye could see. All right, so again, this number that it came up with is just because I hit equals twice, and this calculator just keeps calculating. So this answer would be 55.9. All right, so this is 55.9, and of course, because the distance was in kilometers, the size of the object is also in kilometers. All right, so this, with the limit of the human eye being 0.5 arc minutes, which turns out to be 0.0083 degrees. We know the distance to the moon. It turns out that the human eye could barely, I want to emphasize barely, and what I mean by that, by the way, the human eye could resolve it by itself, right? Obviously, with binoculars or a telescope, you can resolve objects much, much smaller. And obviously, the more powerful the telescope, the better that we can do. All right, but the human eye by itself could resolve stuff. down to about 56 kilometers across. All right, so that's of course what this number is. All right, so there is number 3. Let's do the next problem. All right, number 4 says, what is the average density of our moon in grams per cubic centimeter? And this, by the way, this is going to be very similar to our moon rock problem, but now we're talking about the entire moon. The radius of the moon is 1,737.4 kilometers, and the mass of the moon is 7.35 times 10 to the 22nd kilograms, round to one place past the decimal. All right, so you can see there's the answer, 3.3. Now, how do we get that? All right, so of course we start with the density equation, right? The density rho is equal to the mass divided by the volume. All right. Now the mass has to be in grams. All right, so let's work on that one. That's the simplest one. So the mass is in kilograms. All right, so here it is. The mass is 7.35 times 10. So I'm going to just use the e. 10 to the 22nd kilograms. Right, kilograms. And so in 1 kilogram, right, the metric prefix k literally means times 10 to the third. All right, so that's going to be e. So it's, you can just say e to the third, or one times e to the third grams. All right, so so the kilogram part cancels, and so 10 to the 22nd times 10 to the third. When you have that, it's the same base. All you do is you add the exponents. All right, so it's the same number, 7.35, but now it's going to be times 10 to the 25th. Right? Because you just add the exponents, and that's grams. All right, so that one's very easy to do. All right, for the next one, we have to first of all convert the radius from kilograms to from kilometers to centimeters. All right, all right. So here's r. The radius of the moon in this case is 1,737.4 kilometers. All right, so now I'm just telling you that this is a much simpler way of doing this. I'm going to do the steps, but it's basically you just to change it to centimeters, you just say times 10 to the fifth. That's it. Let me just show you why that's true. All right, so 1 kilometer is 10 to the third meters, and then 1 meter is 10 to the second centimeters. All right, so that, do you see that? So the meters cancel, the kilometers cancel, and so you just change it by multiplying by 10 to the fifth. All right, so this is the radius. It's going to be 1,737.4 times 10 to the fifth centimeters. And then what you do is you take that, you use the volume of a sphere. The volume of any sphere is 4 times pi divided by 3 raised to the, r raised to the third power, which I've done right here. And so you get a volume of, here, let me show you in the calculator real quickly. I'm running out of time. It's right here. All right, so that's not in scientific notation, but that's what that's times 10. That's 2.19 times 10 to the 25th. All right. At any rate, so here. So what I'm going to do is I'm going to take. All right. So I'm storing the volume. Right. So see, that's stored right now. So see, watch it when I hit recall. There it is. All right. And what I'm going to do is just type in divided by